Starting lecture 46. In fact, we are now switching over to the other part, the second part of the lecture series. The first part was on devices, device physics mostly. The second part was on MOSFET device models for circuit simulation. It is device models for circuit simulation. Okay. As I said, let us take the case of a simple MOS inverter. Or take the case of a common emitter amplifier. This is called the BJT circuit. It could be a switching circuit also. Intentionally I have made it analog. This is an example of simple circuit blocks. The one is the inverter, which could be extended to NAND gate, NOR gate, and other kind of things by combination of these transistors. Okay, so you see that I started with simple examples of rather very simple circuits. One is a digital inverter circuit using MOSFETs. The other is a simple inverting amplifier circuit using a common emitter configuration of a bipolar junction transistor. Okay, so this is a BJT circuit, analog in nature, and this is a MOSFET circuit, MOS circuit, digital in nature. Now, when I want to analyze this circuit, what is to be done? Normally, what is to be done? I must know the equations for these devices, three devices. In the case of N MOSFET, which is the driver one, the other MOSFET, which is the load transistor, and in this case, the single BJT. I must know because it is a three-terminal. In fact, MOSFET basically a four-terminal device. If I think of VBS, the substrate bias, otherwise it is a three-terminal device. On the other hand, BJT is strictly a three-terminal device, and I must know how the current in the three terminal currents, in this case IC, IE, and IB, and in this case ID, IS, and maybe IG. IG is not important at all, you have seen, particularly only ID, how they are dependent on the voltages between the terminals. What we do, we have already done so, and in your undergraduate classes as well as here, you have been able to develop some equations which relate these currents with the terminal voltages. Okay. So far as these three units or components, which are called active components of the circuits, we know relations we have analytical equations relating the currents with voltages. But remember, they are not simple resistors or capacitors. They are not two-terminal devices. They are three-terminal. Here, in fact, they are four-terminal. In fact, the fourth terminal will be felt for the load rather than for the driver, because in this case substrate and source shorted and grounded. But in this case it is not so. Substrate is grounded because the entire semiconductor substrate normally is grounded, on which all the components are developed. But the source and substrate are not shorted. So therefore, basically it will behave as a fourth term. That is why you have seen always in equations now VBS is appearing in addition to VDS and VGS. VBS was appearing. But in this case, strictly three-terminal device. I know how the currents depend on the voltages, and so far as the analysis of the circuits are concerned, what is the methodology we use? We use the so-called Kirchhoff's current law, KCL, or Kirchhoff voltage law, voltage equations. Say there are two basic approaches. One is called nodal equations approach. The other is mesh or loop equations approach. These are very simple examples. But anyway, always you have to follow those kinds of approaches. You have to write down the equations of I1, I2, or V1, V2, V3, etc. Similarly, I1, I2, V1, V2, V3. That means the nodal equations or the mesh equations or loop equation, where these things, these components have to be represented either by a simple equivalent circuit, and that is possible for small signal incremental behavior of the device. You remember that you have already done that in your undergraduate classes, that any semiconductor device for small applied voltages or for small applied currents at the inputs, in addition to the DC bias called quiescent condition, okay, operating condition, over and above that, when you apply a small, very small AC value or incremental value, the corresponding response in the circuits, in the different other parts of the circuit, the output and different other components, the deltas, the changes in, say, here in ID due to a small change in VG, here in the IC due to a small change in IB, this small delta IC or delta ID or delta VD, whatever the case may be, they are linearly related to the input change. And this is true only for very small incremental signals. In that case, we can represent these devices with the help of some equivalent circuit, linear equivalent circuits. Only difference is there are certain current sources or voltage sources which are either voltage dependent or current dependent. You remember that. So that once we have a circuit where there are resistors, capacitors, inductors, etc., which are passive components, and we know how the current voltage are dependent into them, across them or through them. And in addition to that, we can represent these devices by the linearized models. These are called linearized model, linearized equivalent circuit, which thereafter the task is rather. So you have the entire book of Millman-Halkias kind of books which you have gone through. They are dependent on this kind of approach. When we analyze a transistor circuit, small or big, we represent the transistors by their AC equivalent circuit. To start with, we use the simplest equivalent circuit called H parameter. Thereafter, we go to the more physical circuit called hybrid pi equivalent circuit, or sometimes for very high frequency analysis, we prefer to use Y parameters, S parameters, and so on and so forth. But these are all linearized models. Please remember, these are all linearized models, so the analysis becomes rather simple. But when in practice, there are two things to be understood. One is practical circuits will not be that simple. just not consisting of 1 or 2 transistors or 5 transistors. Particularly IC chip consists of hundreds to millions transistors and so many components. Secondly, I have to do an analysis, 3 kind of analysis. One is called DC analysis. That is very important. When you apply a certain VCC, which is maybe say 5 volt or 12 volt, or VDD, which is maybe 5 volt or 3 volt, here in these 2 examples, then I must know what are the voltages across the devices, across the different terminals of the devices. I must know what is the VDS, VGS of this device, VDS, VGS of this device. When you apply a VDD, say 5 volt, how can I get that? Suppose VDD is 5 volt, but I have to know what is the VDD, VGS, VDS, VGS of the 2 transistors. Unless I know that, I do not know what is the ID against ID, because I have developed equations of ID with respect to in terms of VDS and VGS. Okay, so I have to get the values of VDS and VGS. So what will be the approach? I have to write down those equations, solve this thing, and therefrom I have to find out what is VDS, VGS, etc., etc. So what is to be done is simply I have to write down some equations of currents as functions of voltages, and those will be used for deriving the expressions or values of the terminal. So for all, I have to know what is the voltages across each resistor so that I know the current. I have to know what is this voltage, what is this voltage, what is this voltage, so that I have to, because these devices are characterized by their equations. So there, in the DC analysis, when I am interested to get the DC operating conditions for a given bias, VDD, it would be VSS also. Sometimes we apply some 2.5 volt here, minus 2.5 volt here, 0 volt here, minus 5 volt here, depending on different applications. Okay, I have to know what are the voltages, DC voltages at the different. This is called DC analysis. The DC analysis will require simply I have to use the steady state current voltage equations, relations of the different devices. Steady state means the DC. And under DC condition, what is the current voltage relationship? So DC analysis will require those equations which you have derived, and in fact models also do the same thing. When I consider a large circuit, this is for simple thing, I can do it easily. There is no need of any complicated procedure. When it is a large circuit, what I have to do? I have to formalize the whole thing. I cannot do it just like that by following the textbook kind of approach, the problem solving approach which you normally do using calculators, etc. That will not do, because the number of components is so large. I have again to find out the ways and means to find out the DC voltages across the different terminals using a computer aided approach, computer aided simulation or design approach, okay, so that I can get these values very quickly with very little turnaround time. Next task this thing should do is the analog, and that means the linear analysis. Linear analysis means again the small signal AC analysis, because when I use such circuits for linear applications, I apply normally a small signal, because my main aim is to get an undistorted output. When I apply a sinusoidal voltage at say 100 kilohertz at the input, maybe of very small magnitude, I need that same 100 kilohertz sinusoidal shape to be maintained at the output, amplified or processed in any other fashion, and that needs the linearization of the circuit. So again, that condition must be satisfied, that your input voltage swing should be very small compared to the DC bias there. And for that, also either you can use the so-called hybrid parameter or hybrid pi models and develop the big things, and you can write down. It is not difficult. In fact, students initially that the circuit simulators were developed like that only. Some people use H parameter equivalent circuit, some people use hybrid pi model. And I wrote down it, and then it is a pure circuit network analysis approach. Such simulators were available, network simulators were available earlier. You just define the different components, etc. It was not a difficult task. But then here what we need, we had to do a DC analysis where those equivalent circuits will fail. The AC equivalent circuit will fail for the DC analysis. You have to find out some means to solving that. I have to perform the AC analysis. Then I have to also find out, say, signal handling capacity. You just remember things, signal handling capacity. How to find out from the AC equivalent circuit? Can you find out? Do you remember the signal handling capacity? You remember signal. It is the maximum input signal for this amplifier, above which the output start distorting, or the output voltage versus input voltage curve, which is a linear relation, Vi0, Vo0. As Vi increases, Vo should increase proportionally, but above a certain voltage, that proportional rate of rise stops, and there is a sublinear rise. Vo starts saturating above a certain Vi. At the same point, you will find the output signal starts getting distorted. Input signal is AC sinusoid, output slightly starts and finally it gets clipped. You have seen in op amps and different amplifier applications. So can you use the so-called equivalent circuits, those equivalent circuits for that, because they are valid for only small signal AC. Next task, we have to do the transient analysis. Transient analysis is needed for digital applications. When I have to make a transient at the input from 0 to VDD or any voltage, and I know the nature of input rise, it may be a sharp rise or it may be a rise at a certain predetermined rate. I must know how the output is varying with time. This is what is called transient analysis. And this transient analysis, again, the small signal equivalent circuit, whatever you have used, will totally fail in. Some attempts were made intermediately for large signal analysis, but they did not work well. So ultimately, because our requirement is to find out the DC levels of a complex circuit, I have to find out the linear behavior of the circuit under a small input signal. Sometimes we need that, particularly for analog circuits. I also have to find out the timing behavior, timing waveforms, or it is called what is known as this transient behavior of these circuits for digital applications. And I have to find out, therefore, now a model or models of these devices which work for all these three conditions: for determining DC parameters, for determining AC behavior, for determining transient behavior. For all these things taken together, I have to find out certain ways and means, so-called models. These are called models. I have to find out certain good models for these transistors so that they work for all these three conditions. And that's how the models concept came. And a very efficient circuit simulator, all of you are, I'm sure, have heard of it, SPICE. There are other versions, but SPICE is very famous. And this very efficient circuit simulator, is based on certain device models, and it has become a standard now almost. Other companies have made some changes, etc., but the basic circuit simulator is a SPICE. PSPICE for using in the PCs, ordinary PCs. Similarly, there are other versions of spices. Every company has upgraded spice, and this circuit simulator, they accept these devices using certain approaches. We'll discuss in this class what are the models which spice accepts. This is our thing. There are hundreds and thousands of models published in the literature. We will not go into that. We will consider only those models which are accepted by spice for running spice. We will start with MOSFET. Though we started with bipolar in our chronological order, but while model treatment, we will start with MOSFET and then go back to, in fact, we will be going to BJT in the next phase. MOSFET models were developed in different phases, okay, depending on the chronological. You know, say, for example, in 1968, Sickman actually, and D.A. Hodges. That was the beginning of MOSFET, LSI MOSFET. They proposed some models for spice simulation, circuit simulation. Spice was developed a long time ago. And those models later was called level 1 model. These are valid for N MOSFET and P MOSFET, therefore can be combined to analyze CMOS. And that is due to these two famous professors. And you have already, in fact, all these models are already derived in the class while doing with the physics of devices. So I will not go into, only I will give you some salient things. For example, in level 1, which is based on the simplest MOSFET current voltage relation. You remember I told initially I derived an equation where I said that it is where drain induced depletion was ignored. I assumed that the depletion layer is uniform in thickness below the gate, and that value is Dmax, and that's how I derived an equation for ID which appeared to be a rather simple equation. That was the starting. In fact, level 1 follows exactly the same thing. But here the symbols etc. are a little bit different. So I will request you that whatever equations I write here with little bit modified symbols you will find, you compare with my previous lectures for the simple model and the more exhaustive model, which I have discussed at length in quite exhaustive details in the class. It will be very much clear to you in that case. Say in level 1, for example, threshold voltage, we call it VTH because they call it VTH in computer data. VTH, instead of VT, it is written VTH, not VT small h. Small t small h is thermal voltage. So VTH, the threshold voltage, is VFB plus twice phi p plus gamma signs are also different. I am explaining that. am coming to the COX dashed. Sometimes I'll write down what we wrote earlier. We use CI earlier because I made a general analysis. But these people, they are technology people. The model people were technology people, and oxide was a standard dielectric, so they preferred to use oxide, COX. COX dashed, why dashed will be brought afterward. Finally you will find it is only COX. But here I am writing it COX dash for certain reason, and which is nothing but the insulated or gate dielectric capacitance per unit area. Gamma, you just see it is the same equation which we write normally. Here, the gamma parameter which comes like this, 1 upon COX square, is just standard thing I write, QB by COX, QS by COX, isn't it? That was the time of, this is actually, what is it? VTH is equal to VFB plus V across insulator, VI or VOX, plus psi s, the surface potential. At VT, psi s is twice phi p, which is I am written like this. And this is equal to Q, and VOX was equal to QS divided by COX. And QX was root over twice Q, the same thing. You just compare. Only thing is now I have introduced the effect of the substrate bias. Earlier in our analysis we have used plus here to avoid complication. I told you very clearly why. Because usually the substrate bias is reverse. Rarely, very rarely substrate bias is forward bias. So in that case, if I know that this is the substrate bias, why unnecessarily keep the sign convention? Then unnecessarily we have. So therefore I wrote BBS, but then I prefer to use a modular sign here. But then it is a general formula where VBS is the voltage at the body with respect to the, so body means bulk, substrate with respect to the source, okay, and body is P for NP, NMOS body is P silicon, and source is N plus. So P positive and N plus negative means forward bias. So if we apply a little forward bias, this will be, this minus sign is, that means this is plus then. Whereas when this will apply reverse bias, which is the usual case, it becomes negative, so effectively it becomes twice phi p plus VBS. So normally VBS is negative, to be kept in mind. VBS is negative for reverse bias. And positive for forward bias, to be kept in mind. This parameter in the SPICE literature catalog, it is called body effect parameter, because it is this gamma, and VBS, body effect means how VTH depends on VBS. It is a coefficient is involved in that, and that is gamma. That is why they call it body effect parameter. VFB, as before, is phi ms minus and QO dashed, which is the same thing as QF in our earlier analysis. QF in our earlier analysis, fixed, that is the fixed oxide charge density, surface density. That means fixed oxide charge per unit area of the surface. This is how they modeled. Here, phi ms in level 1, phi ms is defined, is given, is a parameter, and qo dash is also a parameter. Okay, and in that case, IDS, if you remember the derivation, I am not repeating the derivation, is given by, they use only mu, because they want to keep the analysis general, so instead of writing n or p, they write mu. You remember this simple equation we derived earlier, rather simple equation, where this L effective means, normally we do it like this in SPICE modeling. We use this kind of geometry. Always, we earlier in our equations we have dropped the S, but here I am always writing with respect by S. Here stands for source. Please remember that S stands for source, not for substrate. Stands for source. S stands for source. These are the geometrical things which are considered in SPICE models. You see that L is the gate length defined by the mask. L is the gate length defined by the mask. You remember the polysilicon gate has to be, polysilicon or aluminum gate has to be defined by lithography. And there that poly gate has a width or a so-called length. That length is the channel length as defined in the mask. Thereafter, when you do the implantation and annealing to the thin oxide, there will be a little lateral diffusion. So junction will not be exactly, I told earlier. For simplicity, we consider the junction to be cylindrical for analytical simplicity. But when I implant, when I diffuse the junction, it is more or less cylindrical or semi-cylindrical, little bit, slightly, 80%. Normally, for a diffuse junction, the lateral diffusion is roughly 80%, 0.8 of the vertical diffusion. However, when you implant, the lateral diffusion is extremely small. That means xj1, which is called lateral diffusion, is very small compared to xj, the actual junction depth. Okay. L effective normally is defined as the effective channel length between the edges of, in our analysis earlier, this distance we always wrote as L. But L effective we wrote, this L dash we wrote as L effective. You remember, you please compare or don't be confused. That is why from the very beginning I am telling you that this is the distance between the edges of source and then diffusion at the surface. That is usually called in literature L effective, whereas the L is the gate length defined in the mask. So this is very important. So, and L dash is the channel length after pinch off. In a strong inversion design, you remember there is a pinch off design, a small pinch off region, where Qi is equal to 0, the inversion charge density is 0, and this L dash is smaller than L effective, and this is what is known as the channel length modulation effect. Earlier I have defined it. So please note that this. Now, VD set is equal to VC at L dash. This is a simple thing we assumed in our simple model. At this point, the effective voltage between this is VGS minus VDS, and that is equal to VTH. So VD side is equal to, it is channel voltage, VC as a function of X. I am coming to that. Channel voltage at X is equal to, it is X is equal to 0, this is X is equal to L dash. At X is equal to L dash, and that is equal to VGS minus VTH. And we assume earlier in the simple model that for VDS greater than VD set, IDS is independent. Of VDS. That means perfect saturation. Then in that case, this is the equation for the linear region for the simple model. Then in saturation, it becomes by substituting VDS is equal to VGS minus VTH. That means this value of VD set, we get where beta you know that here I have written L effective. This L effective is nothing but always earlier we have written W by L, but that L is replaced by L effective. So it is very clearly defined in the diagram. So mu COX dash, this product normally is defined as a term, as a parameter in K suffix P, but actually in computer language it is written as KP, in alphabetic language, KP, and that is called trans conductance parameter. KP is not the product of K and P. KP. Then in linear region, you are still continuing with level 1. In linear region of operation, for which VGS must be more greater than VTH, otherwise the diode transistor will not conduct, and VDS is of course less than VGS minus VTH. The ID equation can be written as in the language of SPICE as W divided by because SPICE lists L. SPICE parameter input list also contains XJ1 and W and KP. So all these parameters are SPICE parameters. So this is the same equation rewritten, only these two product is term replaced by KP and L effective is replaced by L minus 2xj1. L minus 2xj1. These are all SPICE parameters, and it is. But then, when the level 1 was being used in the very early days of MOS technology, people found that saturation is not an ideal saturation. The curve which I draw horizontal, after experimental fabrication, they found that there is a small rise of current with voltage, even in the so-called saturation region. And they found that after some theoretical discussion, they found it is due to the channel. Because channel length modulation could be understood very easily. The channel length modulation concept came quite a long time ago. But these ideal current voltage equations which you derive, the curves are all saturating beyond that VD set, has to be modified, and then that is why it is called models. It is all not fully based on some complete analytical derivations, but there are some semi-empirical or empirical additions, alterations, or modifications, and that is exactly what is done here. You'll find they put a multiplier here, which is 1 plus lambda VDS, which is otherwise not there. This term is not there in the analytically derived equation. This equation was analytically derived earlier. You'll find exactly the same equation you derived, but they intentionally introduce some kind of additional multiplier, which is 1 plus lambda VDS, to take into account the effect of channel length modulation. Do you understand? This lambda term, this is empirically introduced. Empirically introduced, and by fitting with experimental. What they did, using these equations, they tried to fit with experimental data. Then they found by putting this kind of multiplier, they can match with experimental data a little bit more precisely. Not very precisely, because this level 1 was not that accurate, but some more precision was obtained. But then lambda has to be given. This is called fitting parameter, a model parameter. Lambda is called the channel length modulation parameter. Is just like KPWLXJ1, it is one of the SPICE parameters, and its default value may be 0. Default lambda is equal to 0, because if lambda is equal to 0, you are neglecting the channel length modulation. That is valid for very long channel device. That's how it came, people fabricated 10 micron MOSFET. Gradually the technology approached 5 micron and 4 micron, and they found the effect of channel length modulation. How to take care of that in the simple model? They put this multiplier, and lambda was called channel length. But this lambda value has to be, there is no physical thing was in level 1. No physical model for calculation of lambda was given. Lambda has to be suitably adjusted. Some value may be 0.8 or 0.5, or its value will be, lambda is equal to 0 is the ideal case for no channel length modulation, for very long channel modulation, but then it may be 0.01 or 0.1 or 0.2. Some value has to be given by fitting the curve with the experimental curve. Channel length, it is channel length. Narrower is a channel length.
In large circuit, how do we determine lambda?
In
a large circuit.
That is why I am coming here. Level 1 is the simplest model. Thereafter, the level 2, level 3 will find some more physical models were added, so that we are not so much dependent on arbitrary things. We'll be coming to that afterward. And VTH then, in the language of SPICE, was written as follows. Instead of writing the straightforward equation like this, which we wrote in the beginning, VTH is, this is our equation we wrote, VTH is equal to this. Instead of writing that, we write VTH as, in level 1 of course, VTO, this also I gave earlier. Note that XJ1 is the lateral diffusion parameter. Again, it is a, and VTO is a threshold voltage. It is a threshold voltage for this thing we have already introduced earlier.